For my Chapter 7 reassessment, I did a problem similar to one in the book again, but I used this one because I kind of wanted to make sure I was doing it right. So what I did was change the mass of the block so that I know if the mass is much bigger, then my final velocity should be much bigger than that of the book. So the book uses 3 kilograms as the mass, and the answer that they came up with was final velocity of 2.7 meters a second. So what this problem um, is showing is you got a block, a mass 0.8 meters high, and it's going to fall and interact with a spring that is 0.4 meters high, and the interaction is going to be over once the block is 0.3 meters off the ground, which means it'll only be interacting with the spring for 0.1 meters. And it starts out, the initial velocity is 2 meters a second. And our spring stiffness is 2,000 newtons a meter. So we'll start out with the energy principle. EF equals EI plus W. And from there, we get kinetic final plus U spring F plus U gravity F, which is potential gravity, equals KI. The U spring initial is going to cancel out because it's 0. The spring initially isn't doing anything at all. And U gravity initial plus work, and work is going to be 0 too because there's no work. There's no work happening here. So this can be rewritten as mv squared final over 2 plus mgy final plus kss squared final over 2 equals mgy initial plus mv initial squared over 2. So what I did here was I got everything on the other side except for mv squared final over 2 because I'm trying to find v final, vf. So I want that on one side of the equation, as I do here, and we're multiplying this all side by 2, then dividing it by m, and taking the square root to get rid of all of this except for vf, which brings us straight down here. Let's see. So we're just plugging everything into the formula. The 0.5 is going to be the change in the height from initial to final. So we were initially at 0.8, our final is 0.3, 0.8 minus 0.3, 0.5. That's pretty easy. And the 0.1, this number right here is, like I said earlier, it's the amount of distance traveled that the block is actually interacting with the spring. So once I calculated this all, I got 7.13 meters per second, which, let's see, compared with the problem in the book, seems very realistic, I guess. So I pretty much, took the initial number, blew it up, this initial mass right here, from, the number used in the book was 3, and they got 2.7 meters a second, so it was a change of 0.7 from the initial velocity to the final velocity in the book's problem. And in my problem, once I blew up this mass, the initial velocity is 2 meters a second, and the final is 7.13. So it's a big difference. My answer seems to be pretty much right, I guess.